here is
This call is now being recorded.
from, I think, Eastern Cape. I'm not sure. So in this particular question, the first one is the easiest one to start with. You are given about 25 grams of sodium sulfate, and then what you are required to do is calculate, right? So you have to find the number of moles of sodium sulfate. I believe you would do that in a typical classwork problem, but for this one, it was in the exam as well, so that was a simple 3 marks. And then after, we have to find the number of sodium atoms which are present in 25 grams of sodium sulfate. Right, so let us do that. Five point one. We know that the mass of sodium sulfate this one is one of the first things you learn in stoichiometry. So by now you should be very, very much proficient in finding the number of moles. It's about 25 grams, right? And 5.1.1 requires us to find the number of moles in this sodium sulfate compound. And before we can actually find the number of moles, we must know what the molar mass of sodium sulfate is, right? So to find that, we need our periodic table. So that we can find the different molar mass of each element in the sodium sulfate compound. So let's go to our periodic table. This one right here, right? So, okay, hope you guys can see this periodic table. Sodium is here. It has a molar mass of 23 grams per mole. And then sulfur is there. It has a molar mass of 32 grams per mole. And I think we also had oxygen. Oxygen is just right here. It has a molar mass of 16 grams per mole. So let's go back and calculate the total molar mass of this compound. Right. So we said sodium will have 2 times 23 because there are 2 sodium atoms. Right, 2 times 23 grams per mole plus sulfur has 32 grams per mole plus 4 times 16 for oxygen. So this should give you just punch everything in the calculator as is. You don't have to keep writing everything step by step. But if you want to do that, you can. Then this is about 142 grams per mole. Right. Remember what this means? It means for every mole of every mole of sodium sulfate weighs about 142 grams. That's what it means. So now let's find the number of moles in this compound. Number of moles of Na2SO4 is M over big M. Right. So this gives us the mass we were told is 25 grams. And then we just calculated the molar mass. So therefore, our answer should be 0.18 mole. So in this case, because we're not using the number of moles to calculate any other parameter in this problem, we can leave it as 2 decimal places. But if, let's say, the problem was, usually it's like 6 or 7 marks problem, where you have to use this number of mole to find something else. Maybe you still have to take ratios and whatnot. We will make sure that we maintain 4 decimals. But since this is our final answer and we don't require any further steps, we'll just keep it at 2 decimals. So remember, 2 decimals for final answer. But if this was not our final answer, we still had to use these number of moles to find something else in the question. Then, but 4 decimal places for intermediate steps. Because if you use 2 decimals in these intermediate steps while trying to calculate something else, you won't get the right answer at the end. Right, intermediate steps. Right, so this is our number of moles for sodium sulfate. Now, we are required to find the number of sodium atoms present in this particular compound. Good, let's go there. 5.1.2. We know that the number of moles of sodium sulfate is 0.18 mole, right? Now, we want to find in this entire compound how many atoms, or rather, what they're saying here is how many atoms or particles of sodium are there in 25 grams of sodium sulfate. If you remember very well, we have this constant called Na, which is equal to 6.0 times 10 to the power, 23. It's usually 6.02. Right, it's called the Avogadro's constant. So this constant tells us that for every 1 mole of a substance, we have about 6.02 times 10 to the power 23 particles in that mole of that substance. Right, we did this in our previous lesson. I explained it extensively. So if you want to be reminded, or if you want to remind yourself, you can go back there and check those notes. Now, we have already calculated the number of moles of sodium, right? Sodium sulfate. And we said it's 0.18. So now, if you want to find N of, remember the formula, number of moles of a substance is N over Na, where this is what this question is asking us for, and this is the Avogadro's constant, which is 6.02 times 10. So here, this is the number of particles given a certain number of moles. They would say number of particles or number of atoms. They mean the same thing, right? So now, let us find how many particles of the whole compound are there before we can find how many of those particles belong to sodium, because for now we want sodium. But before we can find the number of sodium atoms, we need to understand how many sodium sulfate atoms are there. Sodium sulfate particles are there in total. All right, so what we would do is we can make N subject. Remember, if you have your triangle here, and we did this triangle as well in our previous lesson, but I can just show you quick. Right, this is what it looks like. So in this case, we are looking for N. So we shade N, and therefore everything else is part of the formula. So we'll take N will be simply N times Na, which is just this part. Right, that's how it works. So we're looking for N, the number of particles according to the question. But now for sodium, we will have 0.18 mole, right? And Na is a constant. It's always given in your formula sheet. You don't have to memorize it, but if you want to, it's a very simple number to memorize. Right, so this should give us It's 0.18 times 6.02 is 23. This is 1.0836, right? 4 decimals times 10 to the power 23. But this is the number of particles of the whole compound and not just sodium alone. We want only sodium. So how do we find the ones for sodium? Good. Let's do this. Since we have about 2 sodium atoms in this case, right? It means to find the number of sodium particles in this particular compound, we can simply take this value and multiply it by 2. Therefore, N is simply 2 times if the question was saying the number of particles, you would have written particles here. But since they said the number of atoms, we'll just write atoms here. Right. So this is just a simple count of how many sodium atoms are in a sodium sulfate compound. So that's how you would do a question like this. Right. So now let us check question number 5.2. So for 5.2, we have this right here. And we did this we did some examples on empirical formula. Right. So now in this particular question, we are just required to find that empirical formula. Okay. Let's do this. So first things first, we are told that a substance contains 40% carbon, 6.67 hydrogen, and 53.33% oxygen. And then the first question is define the empirical formula. If you remember very well, can I take this? Let me see. Let's just bring it here. And then we want the second part of this question. Good. Yeah. Remember what we said. You would say you have carbon, C, and it's given that you have 40% of carbon. And you have, what is this, hydrogen, and you are given 6.67%. And you have oxygen, you are given that it's 53.33%. What you simply do, you take these and turn them into masses. Why is this pen misbehaving? Great. So you turn them into masses. So this is 40 grams. This is 6.67 grams. This is 53.33 grams. When you add everything up, it should give you 100%. Usually, that's what happens. So even if you add everything up here, you'll just get 100 grams. So that means the substance weighs probably 100 grams or whatever it weighs. We've not really been told. So you take them and you translate them into grams like this. That's your first step. Right. Now, let us define what empirical formula is. 5.2.1. So empirical formula, remember we said it's just the simplest whole number ratio of atoms in a compound. Right. If you don't remember that definition, you must make sure you memorize it because they want it as is in an exam. It is the simplest whole number ratio of in a compound. That's basically what it means. So now, let's go to question 2, 5.2.2. In this question, we are asked to determine the empirical formula of the substance. Remember, we can use our table. This table is very nice because you don't have to do a lot of steps. You just write everything in this table. Let's think. You just do this, right? And you do another column. Typically, you would do that. Okay, great. Then it's a simple table. So in this table, you will have your C, right? Your H and your O. These are the given elements of this unknown compound. And then here, you'll put in your masses and there, the number of moles of each of them. And on the last column, that's where you take the ratio. Simplest whole number ratio. Now, for C, we know we have 40 grams. Let me do this. 40 grams. This one was 6.67 grams. And I believe this one was 53.33 grams. Right, so then you take the number or the mole. You calculate the number of moles of each. You know that to find the number of moles here, you'd have 40 divided by the molar mass, which is 12. And this will give you your answer. Here you'd have 6.67 divided by 1 to give you your answer. And there you'd have 53.33 divided by the molar mass. Molar mass is here, remember, m over m. You're just following this formula, this that you wrote here. And then this is 16, right? And then you should get your answer. So let us find those moles. 40 divided by 12 should give you 3.33. And this is definitely 6.67. And 53.33 divided by 16 should give you 3.33 as well. Then you take the ratio. So you take the smallest number of all of these and divide the moles, the smallest number of moles that you found, which is 3.33 in this case, and you divide all of the other ones. So you start with this one, it's 3.33 divided by 3.33 is equals to 1. 6.67 over 3.33. So obviously here the answer you'll get is, it has decimals. Let me see, 6.67 divided by 3.33 is 2.00 something, but you take the whole number, you just make it 2, right? And here you never take the decimals. Remember the rule says, if you have 2.5, for instance, you'll just estimate this to be 3. If you had 2 point, maybe say 4, you can estimate this to be just 2. You always round it off to the nearest whole number. So now, for this one, we'll have 3.33 over 3.331. Right? So this means our empirical formula, let me write it here, is, next to C we have 1, so it's C. We would put a 1 here, but in chemistry we don't put those, we omit them, so you remove that 1. Next to H we have a 2, so we have H2. And next to O we have a 1, so we have O. You don't put the 1 here. That's we always omit that part in chemistry, so you can remove that. So that's the empirical formula in this case. So let's see. If this was 4 marks, just doing this alone would have given you your entire 4 marks. Right. Now, let us go to 5.2.3. This was an exam, by the way. Okay, there's a page here. Let's see if we can do and see. Okay. Now we're going to 5.2.3. If the molecular mass of the substance is 60 grams per mole, determine its molecular formula. So remember, what we just determined now is the empirical formula. It's not a true representation of the actual molecular formula of the compound. It's just a simplified version of it. So to find what the actual molecular formula is, we have been given an extra amount of information. 60 grams per mole is what the molar mass of the actual true molecular formula is. So what we do is, let me see, 5.2.1, 0.3. M for the molecular formula obviously you wouldn't write this in an exam. I'm just writing so that you know what it means. Is 60 grams per mole, right? Which we've been told in the statement. But what is the molar mass of the empirical formula? The one we just found. What is it? We don't know it. So we have to find the molecular mass of the empirical formula. So what do? We say M, our empirical formula is, what is it? CH2O, right? CH2O is, if you use your periodic table, you'll have 12 plus 2 times 1 plus 16. This is about 30 grams per mole, I think. Yeah, it should be. So yeah, 12 plus 2 is 14 plus 16, 30 grams per mole, yes. So now, what you do to find the molecular formula, right? Because now we have this value, right? And then let's do this for your color coding. We just found this guy, which is the molar mass of the empirical formula. Right, so you take the ratio of this guy excuse me, no, you take the ratio of the molecular formula of the molar mass of the molecular formula to the molar mass of the empirical formula. The factor that you will get there right, let's do that. So we call this, let's just call it n factor n. It's not the number of moles, we're just calling it n. You can call it anything. Or let's call it R for the sake of simplicity. R for ratio. Right. So we say M molecular formula, right, over M of the empirical formula, molar mass of the molecular formula over the molar mass of the empirical formula. So what is it? You'll find that it is 60, which is this guy, 60 grams per mole over 30. Then your answer would be 2. Right. So that's the ratio. Then after, you take this ratio and you multiply the empirical formula. Right. This is your empirical formula. And that is this guy. After this, you take the ratio and multiply all subscripts of empirical formula. So this guy, right, so what that means is you do this. Come here, you say C, 1 times 2, H, 2 times 2, O, 2 times 2. Where these 2 is just the ratio R, is 2. And then this will give you the empirical form, the molecular formula. So that is the true ratio of all these atoms in their specific compound considered here. So that's C2H4O. Sorry, this was supposed to be 1. O2. Right. So this is now your molecular formula. Right. So if in another question we have to find the molecular formula again, I won't be as detailed in explaining it. But you have now all these steps that you must follow. Right. Good. Let's move on to, are we done with these questions? Yes. Let's move on to another question, which is this guy right here. So let's see, let's do this. Can paste it here. So a certain organic acid has the following composition. Right. So the molar mass of this acid was determined to be that. So this is another example. I just went to a past paper and took all questions that had to do with empirical formula, finding molecular formula, and so on. So we've already defined what the empirical formula is. Already defined. We won't write this again just to save time. So determine the empirical formula of the organic acid. Right. So 6 marks. Remember what we said. 2.1.2. Always. You start here. You have carbon, 54.55%. You convert this to mass, 54.55 grams. Right? You have hydrogen. Typically, it's always the same elements, by the way. Typically you'll have CHO most of the time. So now 9.09%, you convert this to mass. You just write as is. You don't divide, multiply. There's no formula for converting these percentages to mass. The reason we take them as are and convert them to mass is because we assume that the mass of the whole compound is about 100 gram. So 100 gram, 54% of 100 gram is just 54.55 grams, and so on. Right, that's where this whole thing of taking the percentages as they are and moving them to the masses, that's where it comes from. So this is 36.36 gram. But the reason I'm telling you where this whole thing comes from is in a tricky exam where they decide to test your understanding, they might say the mass of this compound is about, say, 300 grams. And the composition of each element is like this, or the contribution of each element to this mass is that. So what you would do then, you would take these percentages and multiply this 300 to get the individual masses of each element. So in this case, we just assume it's 100 because we have not been told the actual mass. So if you're not told the mass, you just take the percentages as they are and you convert them to mass. Good. Now, let's do our table. Actually, I could have taken the other one, but it's fine. C H O. In case it doesn't fit. Okay. Then we have that. We have that. This might be a bit too big, but it's fine. Then you have your mass, number of moles, simple ratio. Mass, number of moles, and ratio. Good. So mass, remember, at 54.55. So all this is in gram, and this is in mole, and this is unitless. You won't have to write this, what I'm writing here in black, but I'm just letting you know this. You would have to fill in the table 36.36, right? Now let's find the number of moles. For 54.55 divided by 12 will give us number of moles, 9.09 over 1 will surely give us 9.09, right? 36 0.36 over 16 will surely give us a specific number of moles. Right, so 54.55, this would be 4.54, actually 4.55. And this would be 36.36 divided by 16, 2.27. Then you take the smallest number. In this case, the smallest number is 2.27. Right. So you say 4.55 over 2.27. Let me just do this. So that you know. In case you forget. You know that we're dividing by the smallest number. So this should be 2.27 divided by 2.27. 1, right? 9.09 divided by 2.27. You will get 4. The actual answer is 4.004 something something, but you just take the whole number. Remember that. And then 4.55 divided by 2.27. Here we got 2.0 something something, and you just take 2, right? So now we say, therefore, empirical formula is, next to C we have a 2, so it's a 2, right? Next to H we have a 4, so it's 4. Next to O we have a 1, so it's just O. We omit the 1, right? Omit means we don't write the 1. Let me just do yellow. Have these, that, that. Have these, that. There's a 1 somewhere here. Right, so that's how you would do this question. Now, let's go on to the second part of this question, which is this guy right here. 2.2. Aha! Remember, on our previous lesson, on one of our previous lessons, actually, I don't remember which one it was, we talked about hydrous salts. So in this example, we are told about copper sulfate, the hydrous copper sulfate. It has a mass of 7.49 grams, right? Upon heating the sample, remember, for us to liberate these water particles that are in the crystal structure of the salt, we usually heat the salt. So when you heat something that has water or that is moist, the water will tend to evaporate because it turns into a gas and it will evaporate. So therefore, that whatever you had initially will be dry without water. Simple example, if you take your clothes and you put them on the washing line, the water evaporates and you're only left with your dry clothes that you can now wear. So that's what we're doing here with the copper sulfate that is hydrous. We just want to remove this water. That's why they were heating it. Right, so that's the first thing we need to understand, just for understanding. You don't have to know deep things about it. So now the mass of these copper sulfates, so the mass of your clothes after you have hung them outside and the water is evaporated, the remaining mass becomes 4.79. So essentially what happened is you had clothes, okay, you had a t-shirt, a jersey, whatever, you just washed it and you remove it from the water, you put it on the washing line. Before anything happens, the total mass of the wet jersey is 7.49. Now, after the jersey is dry, you find that its mass is now 4.79. What does this tell you? It tells you that it means the difference, the mass of the water is actually the mass of the water plus the jersey minus the mass of the final dry jersey. So this should be, let's see. It's about 2.7. So that's the mass of the water in a hydrous copper sulfate. So we are asked to find the value of N in the formula of the sample. What is N? N is just the number of moles. Okay, let's do it like this. It's the number of moles of these water particles that were in the copper sulfate crystal structure. Right, so if we liberate 2.79 grams of water, what's the number of moles that we actually got rid of? Right. So let's just make sure. Let me remove this. Cut. Oh, it's another one here. Okay, it's fine. Let me just move it down. See. Okay. Great. Now let's find the number of moles of the water. Okay. In H2O, the number of moles of water in a 2.7 gram sample of water, let's see, is 2.7 over, so we know that the molar mass of water is just 2 plus 16, which is 18, right? So you would have to obviously first calculate the number, or the molar mass, sorry, before you can find the number of moles. But because we've been talking about how to calculate that, I'll just move a bit faster on this one, 0.5 mole. Right. This is the number of moles of water in a 2.7 gram sample. But what is the number of moles of copper sulfate in Cu? Before we can actually find it, let's find the molar mass. Remember, we said this 4.79 grams is the mass of the copper sulfate alone after we have evaporated the water. So let's see. I have to remove this. Let me do this and say just to have enough space here. Good. All right, so the number of moles or the molar mass of copper sulfate, you can use your periodic table. We know that for copper, our molar mass is 63.5. Then for sulfur is 32, and so on. So we will have 63.5 plus 32 plus, for oxygen we know is just 16. So what is our answer? 63.5 plus 32 plus 4 times 16. That is 159.5 grams per mole. Let's find the number of moles of copper sulfate in a 4.79 gram mass or sample. You will understand why we need both these shortly. So we said we had 4.79 grams over right. So what is the number of moles? 4.79 even if you make this one 4 decimals, it still gives you something like this. So let's just make it 0.03 mole. Right. So now what we want to understand is what is the ratio of the moles of water to the moles of copper sulfate? Because that is how these two, if you can call them substances or compounds, are actually bonded together. They bond in ratios, the same way we were doing here. We took the smallest, let me do this. We took the smallest number of moles and divided the other moles in the substance so that we can find these subscripts that actually define how many atoms or how many atoms of that element make up the whole compound. So the same thing we have to do here to find our N. Divide and before we proceed, this N, right, defines the whole number of moles of H2O. So now, you would typically do this. If you wanted to follow the table method, but typically I'll just divide everything by the ratio. So you have copper sulfate, and you have right. So what you would do, you take the ratio, which is for copper sulfate, we found that is 0.03 over 0.03. This will give you 1. Right. However, for water, you say 0.15, that was number of moles, over 0.03. This will give you, should be about 5 or 6. Let's see, 0.15 divided by 0.03 is 5. So this means that the N this N is equals to 5. It's the same thing that you would do when you are finding an empirical formula, but the only difference now is since this is not necessarily Let me see what happened. Yes. The N we're finding in the case of hydrous salts is this one next to the water molecule. While for empirical formula, it's a subscript. That's the only difference. So what this means is, therefore, that N that they're talking about there is equals to 5. Right. So that's basically what or how you would do a question like this one. Right. And then now, what does it actually mean? So water molecules typically bond in fixed ratios to salts or to hydrous salts in their crystal structure. So if maybe you found that N is 4.2, you would have to make it 4. And if you found that N is 4.6, you would have to make it 5. Because this always has to be a whole number. Must always. It's the same principle that we used when doing empirical formula. So for every 1 mole of copper sulfate, there are 5 moles of water molecules of water in that hydrous salt. That's what this whole thing means. Remember, if you have issues with understanding such things or you have more questions, you are more than welcome to ask. After the end of the session on the groups, we will be gladly able to assist you. Now, that's how you would do this one of finding N. Okay, let's move to 2.3. Let's see something. Okay, percentage yield. Let's move this one here so that we have enough space. Good. Now, potassium carbonate, which is this guy, reacts with excess, keyword here, excess. Remember what we said about excess, and there's excess and limiting reagents. So it seems like in this problem, we're already told what an excess reactant is in this reaction. So they say the excess hydrochloric acid. So therefore, this guy is our excess reactant. So if this is our excess reactant, it means automatically, in this case, this guy will be our limiting reactant. So pay attention to keywords in problems. And then the rest is just, in one of such reactions, 15 grams of potassium carbonate, right, reacts with excess hydrochloric acid according to this balanced reaction. Luckily, it has already been balanced. Right, so let's just do this. This is okay. Good. So now let's start. Define term 1 mole of a substance. So the official definition that you must always memorize for such question is 1 mole of a substance. It's usually defined as the number of or the amount of substance. Actually, it's the amount of substance having the same number of particles as there are atoms in 12 grams of carbon. So let me write it down for you. So they said 1 mole. That's why you have to use this official definition. If they said what is a mole, okay, the number, right? We said it's the number of, or the amount actually. number doesn't work very nice. Let's say the amount of substance having the same number of particles. Let's see. You should memorize this definition at all costs if you want to get this free 2 marks, right? So what I would typically do when I was still in high school, I would list all the relevant definitions. I would know what it means conceptually, but I wouldn't necessarily memorize it then and there. And then a few days before the exam, after having practiced all the other problems, I would then start going through my definitions. It helped me, but it might help you as well, right? Because sometimes trying to memorize it months before an exam, you'll probably forget it. So just list them down, and then maybe a few days before the exam, just start memorizing it. That actually helps. Okay, so the amount of substance having the same number of particles as there are atoms in about 12 grams of carbon. That's what 12 grams of carbon. It's a simple definition to actually memorize. Right, so let's move on to the calculations now. Calculate the number of moles of K2CO3, which is potassium carbonate. Before we find it, remember, we just need to find first the K2CO3 molar mass, which is, we have to use our periodic table. Potassium is 39 grams per mole. Think we know the other ones, so let's go back. So we'll have 2 times 39 plus 12 plus 3 times 16. Then you can just punch this in your calculator. Times 39 plus 12 plus 3 times 16. This is 138 grams per mole. So therefore, number of moles of K2. Notice I make a habit of always specifying the number of moles I'm calculating. This will help you so that you can keep track of what you've done so far in your calculations. So small m, which is mass, over big M, which is molar mass. And then we were given that 15 grams of potassium reacts. And then 138, 15 divided by 138 is about 0.1. Remember, if you had to go further with the calculation, you'd have to use 4 decimals. Right, but since we're just required to do one step, we can leave it here at 2 decimals. Final answers are always in 2 decimals. Never forget that. Okay, good. Now, let us do the number, determine the volume of carbon dioxide formed at STP. 2 point. Remember, at STP, we have conditions. These will be given to you in the formula sheet. One condition that we have is the molar gas volume, Vm, is about 22.4 cubic decimeters. Right, that's the first thing you have to understand. I think we covered this as well in one of our previous lessons. Now, to determine the volume of CO2, remember, if you are talking excess and limiting reactant, you always use the number of moles of the limiting reactant to find the number of moles of whatever product of interest. In this case, carbon dioxide. Use. Therefore, in this case, potassium will take the molar ratio between potassium and CO2. So this is 1:1. And then the number of moles of potassium are 0.11. We don't know the number of moles of CO2. But since the ratio is 1:1, therefore, the number of moles of carbon dioxide that are formed is also 0.11 mole. Then from this, we can use we've been told that this is at STP. If you remember, at STP, to find the number of moles of CO2, N would be equals to volume of the gas divided by the molar gas volume. This formula only applies at STP. Nowhere else. Don't try to use it anywhere else. It's only for gases at STP. So that means to find the volume, because we've been asked to find the volume, we're looking for this guy. V would be N times Vm equals to 0.11 times 22.4 cubic decimeters. So what does this give us? This gives us 0.11 times 22.4. This gives us 2.5 cubic decimeters. So this is the volume, this is the volume that oxygen occupies at STP. So not just any oxygen, it's the volume that 0.11 moles of oxygen would occupy at STP. That's what it means. Good. Now, let's see. Let's do the last question. So after the experiment was performed, right? Remember, you usually perform an experiment to find the actual yield, right? So after the experiment was performed, it was found that 14.5 grams of potassium chloride was actually formed. Calculate the percentage yield of the reaction, right? The actual mass is 14.5 grams, but this is KCl. Right. Now, what is the mass? Let's do this. So this is the actual mass. Now we need to find M, the theoretical mass, because the actual mass will always be given to you. Theoretical mass you have to calculate. Right. So let's try and find it. We already know that the number of moles of K2CO3 that reacted is 0.11 mole. And we know that we must always use the limiting reactant to find the product of interest. In this case, our product of interest is KCl, potassium chloride. So let's do it. So we have 2 next to this potassium chloride, and you have 1 next to potassium carbonate. Let's take ratios. One, and this one is 2. We already know how many moles of potassium carbonate reacted, and we want to know how many moles of potassium chloride formed as a result. Okay, therefore, in KCl, remember, we just cross multiply. We've done quite a number of these exercises where we have to cross multiply. So I expect you to at least know what's happening at this part of the calculation. So this is 2 times. If you don't remember, you can go back to our previous lesson. 0.22 mole. So this means for every 0.11 moles of potassium carbonate that react completely because it's a limiting reactant, we will have 0.22 mole of potassium chloride that forms. Right. Good. Now, let us find what is the theoretical mass. Therefore, we can say I have a bit of background noise here. I'm very sorry if you can hear that. That's just one of those things. So, I'm not sure what's happening out there. So now, you have N times M, right? Remember from our triangle. You usually have a formula equals to like this. So our triangle will have M at the top, big M here. And then since now we're looking for the mass, we shade it out, and then the remaining bottom, we multiply them. So that's where this comes from, right? Good. Let's find the 0.22 and KCl. We don't have the molar mass of KCl. Let's see if we can find it beforehand. M KCl is, we know that K, I think we found K at some point. Let's see. K is 39. 39 plus chlorine. Chlorine should be around 35. Let's check. Yes, 35.5 is chlorine. 35.5. Therefore, 35.5 plus 39 is about 74.5 grams per mole. So therefore, we can now say we can take this guy. Okay, it's fine. Can move this here. 0.22 times 74.5. This gives us 0.22 times 74.5. This gives us 16.39 grams. So before going to the lab, we would calculate how much KCl we expect to form. So in this case, we would find that we expect to find 16.39 grams. Now, we then go to the lab and do the actual experiment, and we find that we actually form 14.5 grams instead. So what is the percentage yield? Percentage yield, you take the actual formed, actual yield. Actual yield is the mass that we formed there over theoretical yield. And then you multiply by 100 times. Right, so actual yield is this guy. Theoretical yield is that guy. You see? That's what's happening. And then this would give us 14.5 over theoretical yield is the one we just calculated, 16.39. Multiply this by 100, you should get your answer. The percentage yield is 88.5%. This means we formed 88.5% of the mass that we had initially estimated. So the actual mass that we formed was 88.5% of the initially estimated one. So that's how you would do that question. So I don't think we'll have enough time to go through the remaining. We can always do them some other time, or alternatively, I can give it to you as homework. Because remember, our lesson has to end at 8. We won't have enough time to go through the remaining ones for now. But worry not, you can take these as homework, and I want to see if you guys actually practice during your spare time. So now, for the sake of today's, to maintain today's time and so on, this is where we would have to end our lesson. And then consider these last two questions as your homework. The principles we use are the same. All right, so thank you very much for attending, guys. And yes, I will see you on the next lesson. Please feel free to ask any questions you might have, including the homework I just gave you. Okay, thank you very much.